Hey everyone and welcome. Today we're going to break down a teaching strategy that honestly flips the classroom on its head. It turns students from just, passive listeners into full-on active investigators. It's called the Suchman inquiry model, and it's all about tapping into that natural curiosity we all have to build some seriously powerful thinking skills.
This is the big question in education, right? It's one thing to get students to memorize facts and figures for a test, but how do you actually teach them to think like a scientist? To ask their own questions, to hunt for clues, and to really understand the whole process of discovery. So that's the core challenge we're talking about, shifting the entire vibe of the classroom. We want to move away from the teacher standing at the front just delivering information, and instead create an environment where the students are the ones doing the heavy lifting, building their own understanding piece by piece. And that is exactly where this model comes in. It was developed by a guy named Richard Suchman, and it's this really elegant, structured way to take that spark of curiosity students get when they see something puzzling and give them the tools to investigate it in a disciplined, almost scientific way.
Okay, so here's our game plan. First, we'll look at how to unlock that initial curiosity. Then, we'll see how you actually set up the inquiry. After that, we'll dive into the heart of it all, the yes/no investigation. We'll cover how students build their explanations, and finally, we'll talk about the real long-term power of using this model.
All right, Section 1, Unlocking Student Curiosity. The whole thing kicks off with a really simple but powerful idea. People are naturally driven to figure things out when they're faced with a good puzzle.
The process begins with something called a discrepant event. Now, that sounds kind of fancy, but all it really means is you show students something that doesn't make sense. It's a wait, what moment. Something mysterious or unexpected that totally conflicts with what they think they know about how the world works. And that little bit of confusion, that's what creates a genuine need to find an answer.
So here's a classic example, the bimetallic strip. Imagine showing your class a simple straight metal strip. You tell them it's made of two different metals, say steel and brass, that are fused together. Then you heat it up over a flame and it dramatically bends into a curve. That's weird, right? Most things don't do that. It's a simple visual puzzle that immediately gets the brain going, asking that one simple question. Why did that just happen? So once the students are hooked by that puzzle, it's time to set up the inquiry. And this is key. This isn't some chaotic free-for-all. It's a highly structured investigation with some very specific, very important rules of the game.
Now, these rules are really the engine that drives this whole thing. And the most important rule of all is right at the top. Students can only ask questions that can be answered with a yes or a no. That simple constraint is a total game changer. It forces students to stop just asking for the answer and to start forming their own little mini theories that they can test with every single question.
And check out how this totally flips the traditional classroom rules. The teacher's job is just to present the puzzle and be the source of data, the yes or no answers. That's it. No explaining. The students, they become the investigators. It's their job to ask the questions, gather the data, work together, and build the theory that solves the mystery. The ownership is completely on them.
Okay, now we're getting into the real core of the model, the investigation itself. This is where students use that yes or no structure to methodically collect the clues they need to solve the puzzle. The real magic here is in the precision of the questions. A student can't just ask a broad question like, why did it bend? Because that puts all the thinking back on the teacher. Instead, they have to frame sharp, verifiable questions, like, is the strip made of more than one material? The answer? Yes, is a solid piece of data. Every single question becomes a small, deliberate step toward a bigger understanding. And this whole questioning process usually happens in two phases. First up is verification. This is where students just try to get the basic facts straight. Was the strip straight before you heated it? Yes. Was it solid? Yes. Then, once they have the facts down, they move into experimentation. This is where they start trying to figure out cause and effect. If you heated only one side, would it still bend? Yes. Does it matter which metal is on top? Yes. See? They're isolating variables.
So after this flurry of questions, the class is left with a whole bunch of facts. They've gathered all this raw data. The next phase is all about making sense of it, organizing all those yes or no answers into a coherent explanation. So through this whole process, the class builds this shared pool of knowledge. They figured out that yes, the strip is made of two different metals, yes, they're stuck together, it was definitely straight before it was heated, and then they might get to a really crucial fact, maybe by asking do all metals expand the same amount when heated, and getting a no.
Suddenly, they have all the puzzle pieces right there in front of them. And now comes the big synthesis, formulating a hypothesis. A student, or maybe a small group, will put it all together. They'll propose an explanation that accounts for every single fact they've verified. This is that awesome aha moment where they connect all the dots and build a theory in their own words, based entirely on the evidence they gather.
But the model doesn't stop there. And honestly, this last part is absolutely critical. The final step is to analyze the process itself. The class actually talks about their investigation. Which questions were really helpful? Which ones were dead ends? Why? This teaches them metacognition, basically the skill of thinking about your own thinking. It makes them smarter, more strategic investigators for the next time.
And that brings us to the real power of the Suchman model. See, the goal isn't just about getting the right answer to this one puzzle. It's about building a whole toolkit of skills that students can take with them and use absolutely anywhere. When you use this model consistently, you're not just teaching content. You're developing intellectual discipline, creativity, and a real tolerance for ambiguity, that feeling of being okay with not knowing the answer right away. It shows students that knowledge isn't just a fixed thing in a book. It's something we build and revise. Plus, it naturally teaches collaboration, logic, and strategic thinking. These are the skills that matter.
So let's just do a quick recap of the entire cycle. Phase 1, you start with a puzzling problem. Phase 2, students gather data with yes-no questions. Phase 3, they experiment by testing variables. Phase 4, they put it all together and form an explanation. And finally, Phase 5, they analyze their own process to get even better at it. The Suchman inquiry model gives you this amazing, clear framework for turning pretty much any topic, science, history, you name it, into a real adventure of discovery. So the only question left for you to think about is, what puzzling event are you going to use to get your students thinking? And if you want to dig even deeper into this model, these are the excellent sources we drew from for today's explainer. Thanks so much for tuning in.